In this video, I'd just like to continue with some more examples of finding new Taylor series from old. So at this point, we've talked about, or at least seen an example of using just function composition, just differentiation, or finally anti-differentiation. But I wanted to point out another thing that we didn't address specifically, but that you can handle very nicely with Taylor series, and that's multiplying by powers of x or dividing by powers of x. So for just a few examples, if we look at the function x squared cosine of x. So here we can see it's not function composition, differentiation, or anti-differentiation of any of my familiar Taylor series. It's simply just a multiplication by x squared. So I would start with the idea that this is saying x squared times the Taylor series of cosine of x, which again, we can reference our sheet, but that has terms -1 to the k, x to the 2k divided by 2k factorial. And notice that we have this x squared here that does not depend on k, and the idea is that we can bring that in side of the sum here. And in particular, what I'd like to do is lump that together with the x to the 2k that I already have. So all this does is simply changes the power on x inside of the sum. At first, I had x to the 2k. Now I'm multiplying that by an x squared, so I can add those exponents to make this x to the 2k plus 2. By the same token, if we looked at, say, sine of x divided by x, we can think about that as x to the -1 times our Taylor series for sine of x. So writing that in here. And again, I can bring that x to the -1 inside and lump that together with my powers of x that are already present. And that would then change x to the 2k plus 1 would now be, we'd subtract 1 from the exponent. So this would just be x to the 2k. So that's how we deal with multiplying by powers of x or dividing by powers of x. And I want to go just through one more example in this video, almost as like a cautionary example. So multiplying by powers of x is simple, as we've seen above, but multiplying two power series together is a different story. So multiplying two power series together is difficult. So to give an idea for why this is going to be hard, what I'm saying here is that if you try to take the sum of a sub k times the sum of b sub k, so I'm not even talking about power series here, I'm just saying just sums in general, a common misconception is that you can multiply the terms, but it's not true that that product is equal to simply the sum of the product of the terms. To think of why this is true, we can even think of a finite version of these sums. If you were to simply take a1 plus a2 and multiply it by b1 plus b2, that's certainly not a1 b1 plus a2 b2. So this is a more concrete example of the statement that's not true right above it. And notice what's missing is the cross terms. And the more factors I have together, the more cross terms. So by simply just writing this as the sum of the product of the terms, I'm missing a lot of different terms. And so we could handle this on a term-by-term basis, the multiplication. But in this next example, what I want to get across is that that is itself a very complicated process. So in this example, let's find the first 3 non-zero terms of the Taylor series centered at 0 for the function sine of x times cosine x. So the idea here is, again, I can interpret this as a product of the Taylor series for sine times the Taylor series for cosine. However, I as I noted above, can't simply multiply together their terms. So sine of x times cosine of x. If I were to replace them with their Taylor series, this would be equivalent to the sum from k equals 0 to infinity of negative 1 raised to the k, x to the 2k plus 1, divided by 2k plus 1 factorial, and then multiply that by the sum from k equals 0 to infinity of negative 1 to the k, x to the 2k times 2k factorial. And like I said, here this becomes very complicated. Importantly, we're only asked here to find the first three non-zero terms of the Taylor series. We're not asked to find the entire Taylor series. So what I will do is focus on writing out the first several terms of each of these respective Taylor series. And then we're going to have to just think about, much like my last line above, multiplying those through, just almost treating them as polynomials. Oops. So the first several terms of sine of x, if I were to write that out, would be x minus x cubed over 3 factorial plus x to the 5th over 5 factorial, and so on. And we would be multiplying that by the first several terms of cosine, and those are 1 minus x squared over 2 factorial plus x to the 4th over 4 factorial, and so on. So now, if I want to start thinking about what my terms are going to be, my first goal is to find the constant term. And so in doing that, I need to look at, let's color code these, my terms in my green box and my terms in my pink box here. And I need to think of ways in which I can take a term from the green box, multiply it by a term in the pink box, and get a constant. Notice that that's impossible. I would have to have a constant, a non-zero constant in the green box to multiply by the one I have in the pink box, and I don't. So the only constant I would get is 0. And of course, that's not going to contribute to one of my 3 non-zero terms. The next thing I'm interested in is how I can get an x to the first power term. To get an x to the first power term, what I can do is take this x and this 1 and multiply those together. So there's only one way that we can get an x to the first power term here. So this gives me, let me change back to black. This gives me 1 times 1 in terms of looking at those coefficients, x to the first power. Now I look at this and I'm trying to think about how I can get an x squared term. Again, there's no way I can multiply something from the green and something from the pink that's going to give me an x squared term. And in particular, notice that you would always have an odd power when you look at the product, because we would have an odd power of x times an even power of x. Adding those together would always be odd. So again, we get this 0x squared. Now I want to look at the possibility of a cubic term. And to get that, we have to consider what we can multiply together. Notice that I could take x times my x squared term, but I could also take my x cubed term times my constant term. So there are now 2 ways that I can end up with a product that gives me an x cubed. So putting those together, let's see. So we said x times x squared. So that's going to be 1x times negative 1/2 x squared, so negative 1/2. And likewise, we're going to have negative 1 over 3 factorial times the constant 1. So minus, in this case, 1/6. And that's going to be my coefficient. Again, there's no way to get an x to the fourth from what we described before. And then finally, I want to consider my x to the fifth possibilities. And again, we want to consider all of the ways that that could happen. So I could take x and multiply it by my x to the fourth term. I could take my x cubed term and multiply it by my x squared term. Or I could take my x to the fifth term and multiply it by my constant term. So I want to consider all three of those possibilities. So x times x over 4 factorial, that's going to give me 1 over 4 factorial, or 1/24. We have negative 1 over 3 factorial times negative 1 over 2 factorial. That gives me a positive 1/12. And then we have 1 over 5 factorial. And that's multiplied by 1. So this leaves me with the first three non-zero terms of my power series. This would simplify. You could check to x minus 2/3 x cubed plus 2/15 x to the fifth. And I stopped there because we're only asked to find the first three non-zero terms. So what I hope to have demonstrated here is that this is not a simple process. And by going through this example, I want to encourage you to not try to view things as a product in any way where you would end up having to multiply power series together. In the next video, we'll see an example where it might be tempting to view something as a product in this way, but there's an alternative way to connect it back to our known Taylor series that then, of course, avoids this process of trying to find the product of two Taylor series.